Welcome, future welding inspectors. Welcome. This is a special deep dive designed really just for you. We're kicking off our CSWIP 3.1 exam prep series. Now, that's the certification for visual welding inspectors, and we're going to be tackling some really crucial concepts you'll need to get your head around, not just for the test, obviously, but for your actual career. Our mission today, it's not just about, memorizing answers. We really want to give you a shortcut to being properly informed, maybe spark a few of those aha moments, and just make sure you really grasp the why behind everything. So we're going to explore some leading multiple choice questions, discuss the answers, and really dig into why they matter. Let's sharpen our focus then, yeah? Time to jump in.
Exactly, yeah. In welding inspection, having that deeper understanding, it's not just about passing an exam. It's fundamental. It's about safety, integrity, and the real-world stuff. We'll be connecting the dots, theory and practice, to help you build that solid knowledge base.
Okay, brilliant. Let's unpack our first critical scenario then. Something really fundamental. Visual inspection. We often need tools to, enhance our sight, don't we? So here's a question. When a standard like BS EN 16637 allows using a magnifying glass for visual checks, what's the recommended magnification? What's that sort of sweet spot? Are we talking A, X2, B, X2 to X5, C, X5 to X10, not greater than X20? It's a good question because, too little magnification and you miss things, but maybe too much and you get lost in the surface texture, right? What do you think? What's that optimal range?
That's a great point about balance. It's tempting to think more is better, isn't it? But actually, there's a very practical reason to the recommended range. The correct answer is indeed B, X2 to X5. And it's crucial because this range, it lets you clearly say important surface details, maybe tiny cracks starting or subtle texture changes, without completely losing the overall context of the weld. If you go much higher, say X10 or definitely X20, you could end up focusing on, bits of dust or just a normal surface roughness, things that aren't actually defects. You lose the bigger picture. But just X2 on its own might not quite be enough for those really fine indications. So yeah, X2 to X5, that's generally seen as the perfect compromise. Clear enough, but broad enough. Effective visibility.
Right, that makes complete sense. Finding that useful window, not too zoomed in, not too far out. Okay, so we've got our magnification set, somewhere between X2 and X5. Now, what specific kind of defect, maybe one that's hard to spot with the naked eye, are we most likely to catch using this range? What does it really help us find? Let's look at the options again. A, excess weld metal height. B, undercut. C, internal lack of fusion. D, root concavity.
Right, this gets into the practical application, doesn't it? So with that X2 to X5 range, the defect it's particularly good at highlighting is B, undercut. Undercut is basically a little groove, like a tiny ditch, melted into the base metal right next to the weld edge, either the toe or the root. It's right there on the surface, but it can be really subtle. And that X2 to X5 magnification just makes those small linear features pop, makes it much more apparent so you can actually assess them properly, see how tough they might be.
Okay, so undercut is the prime target there.
Exactly. And just briefly on the others, excess weld metal height. Usually pretty obvious visually, or you grab a gauge, right? You don't typically need magnification just to see it's there. Internal lack of fusion, well, that's internal. It's subsurface. Magnification isn't going to help you see inside the weld. That's where NDT, like ultrasonics or radiography, comes in.
Right, different tools for different jobs.
Precisely.
Yeah.
And root concavity, yeah, it's on the surface, but on the root side, it's often more about the overall geometry, maybe using specific gauges. Magnification can help, sure, but undercut is really the classic surface flaw that this X2, X5 range is perfect for identifying clearly. So for you as an inspector, knowing which tool to use and how to use it effectively for specific flaws, that's just fundamental.
Fantastic. Okay, so it's not just using magnification, but knowing what you're likely to find with it. Good stuff. Right, let's shift gears a bit. From looking closely at the surface, let's dive into the recipe itself, the blueprint for the welding procedure specification, or WPS. Absolute vital document. So imagine this. A WPS often specifies a maximum width for each weld bead. The weave width, especially important for CMM steels, carbon manganese steels. Now, if a welder exceeds that maximum specified weave width, what's the most significant potential problem? What could happen? Your options are A, lack of inter-run fusion, B, reduction in HAZ toughness, C, lack of sidewall fusion. D, too low a deposition rate. So think about going off recipe, essentially, making that weave too wide. What's the main risk there, especially thinking about the material properties?
This is a really critical point. It connects directly to the weld's mechanical properties, its long-term performance. Exceeding that weave width limit can have a really serious impact. The correct answer, and often the biggest concern metallurgically, is B, a reduction in HAZ toughness.
HAZ toughness. Okay, unpack that for us.
Right. So HAZ is the heat affected zone. It's the base metal right next to the weld that didn't melt, but got heated up significantly during welding. Now, CMN steels are strong, used everywhere structurally, but their toughness is key. Toughness is the ability to absorb energy to resist cracking suddenly. When you use a very wide weave, you're putting a lot more heat into that area per pass, higher heat input. And for CNN steels, too much heat, held for too long in that HAZ, can cause the microscopic grain structure to grow larger, become coarser. Think of it like maybe like wood grain. Fine grain is strong and tough. Coarse grain can be more brittle.
Ah, okay.
So this coarse grain structure in the HAZ directly leads to lower toughness. The steel in that zone becomes more brittle, more likely to fracture under stress, especially maybe in cold temperatures or under impact. It creates a potential weak spot.
That's a great analogy, the wood grain. Makes it very clear.
Yeah, and just to touch on the others quickly, lack of fusion, interrun, or sidewall, that's usually more about technique, travel speed, angle, maybe not enough heat overall, rather than too much heat from a wide weave. And a wide weave certainly doesn't mean a low deposition rate. If anything, you might be putting down more metal per pass. So yeah, the primary worry with exceeding weave width in these steels is definitely that hit on HAZ toughness.
Okay, that makes perfect sense, the impact on the material's core properties. So sticking with that, this issue of exceeding weave width and potentially damaging the HAZ toughness, thinking practically about the welder doing the job, in which welding position is this problem more likely to crop up? Where is it harder to control that weave width? Consider the standard positions, PA flat dot B, PB horizontal vertical dot C, PF vertical up dot D, PG vertical down.
Yes. This brings in the real-world challenges, the physics, the welder skill. Where's this specific issue more likely? It's generally going to be CPAB or vertical up.
Vertical up. Why there specifically?
Well, think about it. Welding uphill, you're fighting gravity constantly, right? Gravity wants to pull that molten weld puddle straight down. So to counteract that, to control the puddle, stop it sagging, fill the joint properly without getting undercut, welders often have to use a wider side-to-side motion, a wider weave or oscillation. It helps them manage the molten metal. But that necessary technique, that wider weave, inherently means putting more heat into a larger area with each pass. The heat input is higher, and it lingers longer in the HAZ compared to other positions.
Right, because you're moving slower overall, maybe.
Yeah, exactly. Slower vertical progression often goes hand in hand with managing that puddle uphill. So that combination, the wider weave needed for control, plus potentially slower travel, really increases the risk of overheating the HAZ and getting that grain coarsening, that reduction in toughness we talked about. Compare that to, say, PA flat or PB horizontal. Gravity is less of an issue or even helps. Control is usually easier without needing such wide weaves. And PG, vertical down, that's typically much faster travel, lower heat input per unit length generally. So while it has its own challenges, excessive weave width causing HAZ toughness problems is less common there than in vertical up. So yeah, for you as an inspector, knowing that vertical up is prone to this helps you focus your attention, to look closely at the weave consistency and be aware of the potential impact on the HAZ in those welds. It guides your inspection.
That's really insightful. Knowing the why behind the position makes a huge difference. Okay, so that wraps up this focused deep dive into some pretty critical CSWIP 3.1 concepts. Just to recap quickly. We saw why that X2 to X5 magnification is the sweet spot for visual inspection, especially for nailing things like undercut. Then we dug into how exceeding the specified weave width, particularly in CMN steels, isn't just messy, it can seriously reduce HAZ toughness because of that extra heat input causing coarser grains. And we learned that this risk, well, it's significantly higher when welding vertical up, the PF position, because of the techniques often needed to fight gravity. We really hope this session has given you some clear insights, armed you with a deeper understanding, not just ticking boxes for the exam, but for being a better, more knowledgeable inspector out in the field. Remember, knowing the why really is everything.
Absolutely. And maybe just a final thought to leave you with as you continue preparing. Consider this. How can what seems like a tiny detail, maybe just slightly wider weave than specified, or using the wrong magnification setting during a check, how could that potentially cascade? How could it become a significant failure point in a real structure, maybe years later? The precision, the critical thinking, that deep understanding you're building right now, that's genuinely the foundation of structural integrity. It's about safety. It's a big responsibility.
Well said. Keep learning, everyone. Keep asking those questions. We'll be back to help you dive even deeper into more essential knowledge for your CSWIP journey. Until next time, stay curious and keep building that expertise.